Thank you so much for the invitation to speak about the exciting science that we will be doing with James Webb in cycle one. It's very nice to be back at Space Telescope, even if virtual. So I will tell you about how James Webb will be able to shed light on the origin of the famous Crab Nebula. And I would like to acknowledge the collaborators on this project. They are listed in alphabetical order on the left. And a number of these collaborators are here at Space Telescope. So I would like to start out with some background. This diagram that you're seeing shows the evolutionary paths of low mass sun-like stars on the left, and on the right, massive stars that are more than 8 times more massive than the sun. The lower mass stars live for billions of years, and at the end of their life, once they stop producing energy through nuclear fusion, their material is shed without an explosion, producing what we call a planetary nebula. And what remains in the center is the hot core of the star composed of carbon and oxygen, and this is called a white dwarf. Stars that are more massive and their lives vary differently, they have shorter lifetimes, significantly shorter, and their cores are hot and dense enough to continue fusing atoms until an iron core remains. And since fusion of iron consumes energy rather than creating it, at this point in the evolution, the star undergoes a sudden collapse and produces a supernova explosion. And what remains in the center is a neutron star or a black hole. And we call these types of supernova explosions core collapse supernova explosions. What I would like to talk about now is why supernova explosions are important. They are among the most energetic events in the universe, and they drive the chemical and thermal evolution of galaxies, and they significantly influence the galactic structure. Supernova explosions enrich the surroundings with heavy elements from which new generations of stars and planets form, and they create and destroy interstellar dust. They can also trigger formation of new stars. And this periodic table that you're seeing summarizes the origin of elements, color-coded by the mechanism by which they are produced. On the right is the fraction of each category in the makeup of the human body. Everything in orange, purple, and blue is associated with a supernova explosion, so almost 75% of what we're made of. And despite the importance of supernova explosions in practically all areas of astrophysics, there is still a lot we don't understand about these explosions. So for example, astronomers are still piecing together which stars produce which types of supernovae, how exactly those stars explode, and how the explosions enrich the surroundings with gas and dust. And this brings me to the study of supernova remnants. Supernova remnants are remains of supernova explosions in which we're able to spatially resolve the expelled material to learn about the star that produced the explosion. We can use them to learn about the characteristics of the explosion itself, as well as the surrounding environment that might have been modified by the star in the final stages of its life. The Crab Nebula is not only the most famous and well-studied supernova remnant, but it's probably also one of the best studied objects in all of astrophysics. The original supernova that created it was actually observed by medieval Chinese, Japanese, and Arab astronomers. So its age is precisely known. It exploded in 1054 AD. It was discovered as a remnant actually 300 years ago and has been studied ever since. And this year happens to be the 100th anniversary of the discovery of the Crab Nebula's expansion. And the crab was actually the first object that was ever identified to have originated from a supernova explosion. This was back in 1939. So the Crab Nebula in all these years has really served as a benchmark for understanding both neutron stars and pulsars, and also a calibrator for supernova explosion models. So many years of work of many hundreds of authors have contributed to our understanding of the crab, and there is quite a lot that we do understand about this very complex supernova remnant. But even after intense study for all these years, some of the very basic questions remain about its origin. And this includes what type of star produced the supernova explosion and what type of explosion it was. And this is something that we still don't know, but that James Webb will be able to address. And what you see shown in this image here is the spectacular Hubble Space Telescope image of the crab in the light of oxygen and sulfur. The crab has an energetic pulsar in its center. It's a rapidly spinning neutron star with a very high magnetic field. And as this neutron star spin slows down, the rotational energy powers a wind of relativistic, very fast particles that are accelerated in the magnetic field, and they produce radiation. And this is called a pulsar wind nebula. And in this image, you see the pulsar wind nebula as this faint blue glow in the center. This wind nebula is a high pressure, low density bubble that expands from the center into the material ejected into the explosion. And then instabilities form on the surface and concentrate the material into these dense filaments of supernova ejecta. And then the photons from the pulsar wind photoionize that material, making it visible in the optical and infrared. So that's what gives rise to the Crab Nebula that we see today. And this movie put together by here at Space Telescope shows the multi-wavelength view of the Crab Nebula and how it looks like at various wavelengths. So this is the composite image. The radio seen here outlines the regions of the compressed magnetic field. The infrared shows where the supernova ejecta and dust are concentrated. The optical gives us the view of the ejecta, and then the UV and the X-rays that you'll see in a moment trace the very high energy photons from that pulsar wind that I mentioned, and the structure of that pulsar wind mimics the structure of the pulsar's magnetic field. So that's the multi-wavelength view. I would also like to show this recent movie that gives a 3D view of the Crab Nebula, and it was produced by collaborators on this project. And this is actually a three-dimensional reconstruction of the Crab Nebula made from real data over 300,000 individual spectra of the optical filaments. The filaments of the ejecta are confined in this thick shell around the pulsar wind bubble which fills the center. So that is what when you're looking at the filaments, that is what you're seeing in the Crab Nebula. So this gives a really nice three-dimensional view of how it looks. Okay, so what are some of the biggest remaining questions about the Crab Nebula? The main unanswered question is about its origin and what type of star and explosion produced it. The total amount of material in those filaments that I mentioned make up about 5 solar masses of material. And this material has relatively low velocities for a supernova on the order of 1,200 kilometers per second. So when all this material and its velocity is taken together, this only accounts for about 10% of a typical supernova kinetic energy of 10 to the 51 ergs. And for this reason, it was thought for a long time that there must be a much bigger remnant outside of the visible Crab Nebula that we see, and that material would contain the missing kinetic energy. But despite intensive searching for many years, no evidence has been found for significant mass outside of what we observe. And then a consensus emerged that the Crab must have been produced by a relatively low mass star, so between 8 and 10 solar masses, and that it must have had a low explosion energy. And such a low explosion energy can be produced by a certain type of supernova explosion called an electron capture supernova. This explosion is produced from a star with an oxygen neon magnesium core, and this star would be on the border of the mass range of stars that produce supernovae and those that don't, so on the very low mass end of the range. This type of explosion is currently the leading explanation for the Crab Nebula. But actually, there's still some observational inconsistencies even with this explanation. So for example, the pulsar in the Crab, its neutron star, is moving, and it's moving with a velocity of 160 kilometers per second. And such a high velocity or kick to the pulsar would require an asymmetry in the explosion. And theoretical simulations of these electron capture supernovae produce very symmetric explosions and cannot achieve very high velocities for the neutron star. They only achieve on the order of 10 kilometers per second. But then very recent explosion simulations of more typical iron core collapse supernovae on the lower mass end of the mass range were able to produce both the asymmetries that would be needed to explain the pulsar velocity, as well as a low enough explosion energy that might explain the rest of the crab. So this type of explosion may also be a candidate to explain the observed properties of the crab. So this question has still not been settled. And I'd like to mention another mystery with the Crab Nebula, and that is that the historical record of the supernova luminosity suggests a much more luminous explosion than would have been expected from this low explosion energy that needs to be invoked to explain the crab that we observe. So one hypothesis that has been put forward is that there might have been significant circumstellar material present around this original star, and then that the interaction of the supernova shock with that material could have produced a high luminosity of the supernova that was observed. And indeed, these equatorial filaments running east-west in the crab, do have a different chemistry and are more helium-rich than the rest of the nebula. And the pulsar wind also appears to be pinched along that plane, as if there's dense material surrounding it. So the question is whether this is evidence for some pre-existing circumstellar material in this region, and that is also a question that has not been settled. So here is a summary of these open questions that James Webb will be able to address. So first, it will be able to address what type of explosion produced the Crab Nebula, and whether there is evidence for significant circumstellar material that might explain that supernova luminosity. And related to that, James Webb will be able to determine the type of dust that formed in the Crab Nebula and where it is located. And through that, we would study the any presence of circumstellar material. So I would like to go through and address each of these questions and tell you how James Webb will be able to do that. The models for the electron capture supernovae that I mentioned and iron core collapse supernovae predict very different ejecta distributions in the remnant and also different abundance ratios in the ejecta. One very notable difference is the ratio of the nickel to iron in the ejecta that would be expected in these types of explosions. And it is different by an order of magnitude between the two different explosion types, with a much higher nickel to iron ratio expected for these electron capture supernovae. And previous measurements of this ratio have been highly anomalous. And one of the primary reasons for that is because of the very complex ionization structure in the filaments in the Crab Nebula, and that could not be spatially resolved previously. And James Webb is uniquely suited to provide accurate measurements of this ratio on spatial scales that actually compare to the physical sizes of the dense filament cores. So providing more accurate measurements of this ratio while resolving the ionization structure. And James Webb will also provide high spatial resolution iron distribution maps for the Crab Nebula. And these iron core collapse models predict that heavy elements like iron would be distributed more asymmetrically than for electron capture supernovae, with more material by mass distributed in the direction opposite of the pulsar motion. So this will provide an additional test for the crab's origin. If there is dense circumstellar material present in the crab, that could explain that high supernova luminosity from the historical records. Its signatures would not only be present in the chemistry of the ejecta filaments, but they would also be present in the quantity and spatial distribution and chemistry of the dust that formed in the filaments. There is evidence that rapid and very efficient dust formation occurs when supernovae interact with dense circumstellar material. So if that material was present in the crab in that equatorial region, we hope to see differences in the dust composition and distribution in those regions compared to the rest of the nebula. So this brings me to the next major aspect of what James Webb will provide for the crab. It's also uniquely suited to provide the very first map of dust emission for the entire Crab Nebula and to also identify the composition of dust for the first time. So why couldn't we do this with previous observations? If you look at the Spitzer Space Telescope image of the crab that is shown in the bottom corner there, you will notice the pulsar wind emission in blue, and then the ejecta emission and the dust emission in red. And all the imaging filters that contain that emission from dust also contain very bright line emission. So the two could not be disentangled in previous observations. And as I will show in about a slide or two, James Webb can uniquely disentangle these various components. And we also hope to finally identify the dust composition in the crab and search for any differences in composition between the north-south and those equatorial filaments. The spectrum of dust in the crab has been detected at longer wavelengths where the spectrum is featureless and doesn't actually reveal anything about the composition at those wavelengths. The challenge is that the pulsar wind emission, that emission shown in blue, is so bright, shortward of 20 microns, that it completely dominates and drowns out any identifying dust features at those wavelengths. And because of the spatial resolution of JWST, shortward of 50 microns, observing imaging with James Webb will, and particularly spectroscopy, will lead to a reduction in that underlying pulsar wind component by a factor of 50 or so. And this is because the pulsar wind emission has a fairly uniform surface brightness, and the dust emits from very compact filament cores. So increase in spatial resolution drastically reduces that relative contribution from the pulsar wind emission. So the spatial resolution of the MRS spectra in particular will make it possible to observe any dust features and identify the dust composition. And this is a summary of the James Webb observations that we will obtain. There will be MIRI imaging in 4 different filters and then NIRCam imaging in 2 more. The 4.8 and 11.3 micron bands are dominated by the emission from the pulsar wind, and they will be used to model and subtract this component from the other bands. The 5.6 and 1.6 microns filters will map the iron emission in the crab. And then the 18 and 21 micron filters will provide a map of dust emission across the entire crab nebula, something that we have not been able to do before. And then MIRI MRS spectroscopy will be obtained in 2 bright filaments, one in that equatorial region and another from a bright southern filament. And the locations of the MRS spectra are indicated there with the black squares. These are the footprints of our imaging mosaics with MIRI and NIRCam so that you can see what they look like. And these images give an idea of the dramatically improved quality that we will be able to achieve in the mid-IR with JWST. The image on the left shows that spectacular Hubble image that has been approximately convolved to the resolution of the 21 micron filter on a MIRI. And then the image on the right is the existing Spitzer image at 24 microns, showing the combined emission from the pulsar wind, bright oxygen lines, and dust. So the high resolution dust emission map that we will produce will have the resolution of the image on the left, and it will make it possible to correlate the sites of dust formation with the chemical content of the gas filaments that was observed with Hubble and also with MIRI and NIRCam. This plot demonstrates how we plan to produce a dust map. The pulsar wind emission, which is everything below the red shaded region, so it follows a power law, so it's everything that you're seeing up until the red part, that will be subtracted using a model constructed from the 11.3 and 4.8 micron images. We will then be left with everything that is shaded in red, which includes continuum emission from dust and bright line emission from different elements. Then the images from these conveniently overlapping 18 and 21 micron filters or MIRI will be subtracted from each other to give the red hashed region that you will notice on this plot. And that red hashed region is dominated by dust. So the key here is that the very bright line of sulfur 3 will be completely subtracted out. And some of those other less bright lines that you see only contribute about 4% to the remaining flux density when you take this difference of images. So this will, for the first time, give us a map of purely dust emission for the entire Crab Nebula. So just to summarize, James Webb will discriminate between competing models for the origin of the Crab Nebula to reveal what type of star and supernova explosion produced this famous object that has been studied for 300 years. So we are extremely excited for the launch and all the exciting science that we'll be able to do in cycle 1. And thank you again for having me, and I'm happy to take any questions.
So for someone like me who is not super familiar with the literature on supernova remnants, I mean, is this, you say this is the best studied object, but I mean, are there studies of comparable depth and resolution and understanding of other supernova remnants?
So there are many supernova remnants. There are over 400 of them in our galaxy and the nearby galaxies, but there are very few that have the type of resolution and depth and multi-wavelength coverage like the Crab. There are a few others that are intensely studied, probably not as much as the Crab Nebula, but we only have a limited sample of remnants in which we can really dive deep into understanding the composition and the structure, and that provide us this view with very detailed view of how the ejecta are distributed.
Oh, that sounds really exciting. So what's the next step after this study is complete and you've learned what you can from the Crab?
Well, once this study is complete, what this really informs is just that for supernova field in general, we observe supernovae in other galaxies, but they are of course not resolved. So by understanding certain classes of supernova explosions through studying these supernova remnants and using that to inform some of the state-of-the-art simulations for how supernovae explode, we can also use that information to study extragalactic supernovae and be able to classify them and learn how they are produced.
Excellent. Are there other questions? Please type them in the chat if you have them. There is one other question here. It says, will there be any kinematic signatures of different models requiring full future HST observations, for example?
So I'll just speak to that. So we will have, of course, we will obtain kinematic information in just the 2 regions that we are covering with the MRS, not for the rest of the Crab.
I'd like to thank you very much, Tia, for an excellent presentation.